In this video, we cover problem solving associated with the concepts from Chapter 8. A very helpful figure to print out and have available is the periodic table with partial ground state electron configurations listed for it. And this is something that may be useful on the exam as well as in problem solving for ALEX and for your recitation section. We'll start off with electron counts for each of the following elements. We'll look at cobalt, carbon, bismuth, and beryllium. And for each of these elements, let's indicate the number of core or inner electrons, the number of outer electrons, and the number of valence electrons. Reminding ourselves that the core electrons are counted as the number of electrons for the previous noble gas for that element, plus any completed transition series. The outer electrons are those associated with the highest principal quantum number, and the valence electrons for main group elements are the outer electrons for that electron configuration. And for transition metals, they are the outer plus the n-1d electrons for the corresponding electron configuration for that element. So take a moment and try and solve each of these. And once you've done that, then you can check and see the solution. So here we have a table for each of the elements. For cobalt, the previous noble gas is argon, which has 18 electrons, and that's the core electron count for cobalt. The 4s2 electrons in the cobalt electron configuration are the outer electrons, and the 4s2 plus the 3d7 electrons give us 9 valence electrons. For carbon, we have 2 electrons associated with helium, and then the remaining electrons are the outer or the valence electrons, that is the 2s2, 2p2. For bismuth, there are 78 core electrons, 54 from the xenon, and then 10 from the D block, and 14 from the F block. That gives us 78 total electrons for our core electron count for bismuth. Our outer electrons for bismuth are the 6s2, 6p3, and that gives us 5 valence electrons as well. Bismuth is in the P block. For beryllium, we have 2 core electrons, that is 2 associated with helium, and then the 2s2 are the outer electrons as well as the valence electrons. Filled S shell, of course, is not a transition series. Those are valence electrons available for reactivity. And we'll see on the last slide in this video, we'll see how we use the valence electron count for main group elements to determine the common charge states for that element. Next, it's useful to know the order of filling energy sublevels within the atoms, the multi-electron atoms that we're looking at in the periodic table. And in general, we know that as N increases, the sublevels increase in energy, and as L increases, the sublevel increases as well. And as N increases, in some cases, the sublevels can overlap. So for example, the 4s fills before the 3d. But when we're forming ions, then the last electrons in are not always the first electrons out. This is particularly important for the transition series. So the transition metals, they remove their ns before the n-1d. Magnetic properties and the spectroscopic properties of these elements are consistent with this. For the main group elements, the group 1 and group 2, and then the main group metals and the nonmetals, they'll remove the ns electrons or add p electrons, or remove the np to create the nearest noble gas. So let's start off and let's look at a condensed electron configuration for the manganese 2 cation. And then once we have that, we'll draw a valence orbital diagram for manganese 2 cation. In order to do this, we first need a condensed electron configuration for the manganese atom. And for manganese, there's 25 electrons, and that will fill as argon with 18 electrons, and then 4s2 3d5 to get us to 25. Manganese 2 oxidizes by losing 2 electrons, and though the 4s2 fill first, they fill before the 3d5, they also ionize first. So we have an electron configuration for manganese 2 plus cation of argon 3d5, written in a condensed format. Now we need an orbital diagram, and in this case, our 4s's and 4p's are empty, but the 3d's all have an electron in them, and according to Hund's rule, we recognize that they'll all go into separate orbitals, as the 3d are all degenerate, at least in the free atom, in the absence of a magnetic field. And then we'll find that these have a spin that's consistent with 5 unpaired electrons. Now that we recognize this, we can continue on with the magnetic properties of transition metals and, in fact, magnetic properties of metal ions and in general, atoms in general. Paramagnetic species are those with unpaired electrons, and diamagnetic species are those with all paired electrons. So we'll start off, which of the following are paramagnetic and which of the following are diamagnetic? We have some atoms and some ions. So the things we'll need to do, we need to write an electron configuration, and then based on the electron configuration, we can begin to look at paramagnetic versus diamagnetic. If there's an odd number of electrons, of course, the species has to be paramagnetic. But if there's an even number of electrons, then we need to write an orbital diagram to identify whether all the electrons are paired. Now, if there is a filled subshell, for example, S2 or a P6 or a D10, those will all be fully paired, so we would not need to concern ourselves with those. Once we've identified any unpaired electrons, then we can recognize whether we have a paramagnetic or a diamagnetic species. Here's our first 3 elements: silicon, chromium, and zinc. Silicon, its condensed configuration is a 3s2, 3p2, and there's an even number of electrons, and we have a p2, but we recognize from Hund's rule they'll go into separate orbitals because the 3p are all degenerate. Therefore, we have a paramagnetic species with 2 unpaired electrons. Chromium is a 4s1, 3d5. That was one of our exceptions when we looked at electron configurations. If you recall, we might have predicted a 4s2, 3d4, but the spin, it turns out the magnetic properties tell us is a 4s1, 3d5, and this indicates that a half-filled D subshell is particularly stable. So here is our 4s1, 3d5 orbital diagram showing us 6 unpaired electrons. It's clearly a high spin system, what we call high spin. It's paramagnetic. And finally, we have zinc. Zinc is 4s2, 3d10. As zinc is 4s2, 3d10, those are both fully filled subshells. Therefore, all those electrons are paired. We don't need to write out an orbital diagram. We recognize this as a diamagnetic species. Next, we can move on to arsenic, copper-1, and cobalt-3. Arsenic is 4s2, 3d10, 4p3. we should recognize that as an odd number of electrons, and we would know that must be paramagnetic, but we've drawn the orbital diagram just to show us that it has 3 unpaired electrons. Copper 1 has an electron configuration of argon 3d10, and as it is a 3d10, they're all paired electrons. Therefore, copper 1 is a diamagnetic species. Cobalt 3 has an argon 3d6 electron configuration. So we remove the 4s2 and then one of the 3d electrons to give us the d6 valence configuration. And as we see from the orbital diagram, we have 4 unpaired electrons. Therefore, cobalt 3 is paramagnetic. Cobalt 3 is a common oxidation state, but it is not the most stable oxidation state in air. Turns out it's a bit of an oxidizing agent. So it'll return back to cobalt 2 by pulling an electron off of other species. But it is stable and observed in many cases. We also looked at trends in atomic properties within the periodic table, and we had rationalizations for these based on our quantum model. But the most important take-home message is the measurable values, and of course, for atomic size, the biggest atoms are in the southwest and the smallest atoms are in the northeast. So in the lower left-hand corner, when we have cesium, we've got the largest atomic radius. When we get up to the upper right-hand corner, we have helium with the smallest atomic radius. And correspondingly, the ionization energy follows the opposite sense. Large atoms have low ionization energies. Small atoms have large ionization energies. And electron affinities roughly correlate with that as well. Now, there is metallic behavior. In a very rough sense, Silberberg and Mateus describe metallic behavior. And based on this, one can indicate that things that have the loosest electrons, those that are most easily ionized, are more metallic elements, according to his designation. We can use that to understand some periodic properties. This is a rough correlation, though. So let's start off. Using the Silberberg and Mateus designation of more metallic elements, order the following elements in an order of increasing metallic nature. So take a look at this list. We have cobalt, iron, cesium, aluminum, and zinc. So which of these is the least metallic? And then we'll increase from there towards the most metallic. So why don't you try making a list, and then we can compare. So here we have aluminum on the low end, then zinc, then cobalt, then iron, and followed by cesium as the most metallic element. Cesium is the furthest towards the lower left-hand corner of the periodic table. In group 1, the bottom element, cesium is the largest atom and the lowest ionization energy. Aluminum has the smallest radius of this group and the highest ionization energy, and it's followed by the other elements in this list. Next, let's look at the following elements, and we will order them in terms of increasing atomic radius. We have beryllium, calcium, fluorine, and rubidium. So you can take your periodic table and make a list of these. So the smallest element in this group should be fluorine. Next up will be beryllium, then calcium, and finally the alkali metal towards the bottom of the periodic table, rubidium. Now, we also can look at the acidity of the corresponding oxides for various elements. As we saw earlier, more metallic elements have alkaline or basic oxides, non-metal or less metallic oxides form acidic oxides. So for these three elements, arsenic, gallium, and bromine, consider their most highly oxidized form. And so there was a table we saw that listed the range of oxidation states. And so we would want the most fully oxidized form for arsenic, gallium, and bromine. And then we'll consider which one is the most acidic first. So now the most acidic will be bromine. That is the form Br2O7, dibromine heptoxide. Turns out when you put that in water, you get perbromic acid, which is a strong acid, and that is indeed the case. Bromine, of course, is the least metallic of these three elements. It's the furthest over towards the right-hand side of the periodic table. It is a halogen. It is a non-metal. Next over is arsenic. Arsenic forms As2O5. In this case, that is going to be designated as arsenic 5 oxide because it is a metal oxide. It's an ionic oxide. So arsenic is metallic. It's a main group metal. And if you take As2O5 and put it in water, you get arsenic acid, which is a weak acid. More importantly, what you should remember is that arsenic is a more metallic element than bromine. So the information in parentheses is just added. This is not something you would necessarily know. So you won't know that when you put Br2O7 in water, you get perbromic acid, but this information, you'll know it just for your edification, but not for an exam. Finally, we have gallium. And gallium is a metallic element that forms Ga2O3, and that's gallium 3 oxide. Gallium is right below aluminum, and you knew that aluminum was amphoteric. We discussed that and had that on a slide in a previous video. And gallium as well is amphoteric. The lower elements in this series are not amphoteric, but aluminum and gallium are amphoteric. So we see the most metallic element is gallium, and the least metallic element is bromine, and then arsenic is in the middle. So the oxides of each of these elements, we would have bromine, the most acidic, and gallium, the most alkaline. Next, let's look at the positive oxidation states for the following elements. We've looked a lot at oxidation states during this course. We've done redox balancing with cations and anions, and you've been given the oxidation states for lots of elements. But can we look at the periodic table and make predictions for what the common oxidation states will be? And in fact, we can, and we get the correct answers if we use the periodic table properly. So here's a series of elements. Ti, that's titanium, Pb, lead, In, which is indium, Sr, which is strontium, and Sn, which is tin. So let's look at the common positive oxidation states for these elements. And once you see these, I think you'll see that it's not particularly difficult to predict these oxidation states or to simply know what they are. We can identify the electrons that are lost from their electron configurations. So if you are able to write an electron configuration for each of these elements, then you will be able to write down the common oxidation states for these elements because you'll know which electrons are lost. We had that in an earlier slide. So for titanium, the condensed or valence electron configuration is 4s2 3d2, and the first electrons to be lost are the s electrons. So you can lose the 4s2 electrons to form a +2 cation, and in fact that is a stable form. And then you can lose all 4 electrons, that is the s2 and the d2, to form a +4. Those are the common oxidation states for titanium. The most common oxidation states for lead can be obtained from its valence configuration, that is the 6s2, 6p2 configuration. In this case, the p's are lost first to form the +2, and then we can lose the p's and the s's to form the +4. And for lead, the +2 and the +4 oxidation states are the most common. In your lead storage battery in your automobile, if you have an automobile, there'll be lead, and there'll also be lead-4 oxide, sometimes termed lead dioxide, PbO2. And these are interacting, and you see all of these oxidation states, the 0, 2, and 4, involved in the redox chemistry for that system. For indium, we have the 5s2, 5p1 as the valence configuration. In this case, the p can get lost, so that'll be a +1 state, or the p plus the s, and that'll be the +3 state. So for indium, we have +1 and +3 as the most common oxidation states for that element. Indium-1 and indium-3 ionic compounds are common. Next up, we have strontium. The electron configuration for strontium is 5s2. So its common oxidation state is +2, because you lose your 2 s electrons. And finally, for tin, we have a 5s2, 5p2. It's right next to indium in the periodic table, and it can lose its 2 p electrons to form a +2, and it can lose the 2 p's and the 2 s's to form a +4. These are the common oxidation states for these elements. With this, we conclude Chapter 8. In our next video, we'll look at Chapter 9 and start on bonding.